So here's an application, yeah, of the ideal gas equation. So let's just see what we're being asked for. We're being asked, so there are two flasks of equal volume that are connected by a narrow tube of negligible volume. Okay? So each flask contains 1 mole of hydrogen gas at 300 Kelvin and 0.5 atmospheres. One of the flasks is then immersed in a bath, and therefore its temperature is raised to 400 Kelvin, while the other remains at 300 Kelvin. What we need to find out is what is the final pressure and quantity of H2 gas in each flask. Okay? You're given pressure, 0.5 atmosphere, you don't know what the final pressure is. Again, you're given 0.5 atmosphere, you don't know what the final pressure is. Volume, initially the flasks are assumed to be inflexible and therefore the volume remains constant in both cases. Temperature, in one case it's 300, in one case 300 goes to 400. Initially there was 1 mole of gas, yes, in each of the flasks. Finally there's X moles of gas in the first flask and Y moles of gas in the second flask. Okay, that's what we're calling it X and Y. What we need to find out is X, Y, P1 final, P2 final. The problem is now being defined. Let's think about what will happen. Okay, will equilibrium ever be reached if the pressure in the two flasks is different from each other? No way, right? So it's equivalent to saying that you've got a balloon which is full of air at high pressure. The neck of the balloon is open to atmospheric pressure. What will happen? The pressures will equalize, right? Only then will equilibrium be reached. Correct? Therefore, it should be obvious that P1F, so the final pressure of flask 1, must be equal to final pressure of flask 2. This is the one key insight that you need to have from the physical setup of the problem. Okay, how the problem has been set up. So if we have that clear, okay, so that's what we're saying here. P1F equals P2F equals P, right? Some pressure P. Now the gas cannot escape. You know, the moles in the 1 mole in flask 1 and the 1 mole in flask 2 can rebalance between the two flasks, but the total number of moles have to remain the same, and therefore X plus Y equals 2. Yes? Okay, now what happens if we apply the gas equation to the first flask? You get PV, okay, equals, P is the final pressure, remember, and therefore you're talking about the final number of moles, which is X, times R times 300, which is the absolute temperature. You can apply again to the second flask, alright, and since both are talking about P times V, you can equate the right hand sides of these two equations and get equation number 2. Now you've got two equations in two variables. You can solve for X and Y. Okay? Now, if you apply the gas laws to the first flask in both conditions, because volume is constant, so you take the first flask, apply PV equal to nRT and solve for volume. In the first case, in the second case, again solve for volume, but this time instead of 1 mole, it has only X mole. So this is applied to the initial case, this is applied to the final case. If you know X and Y, this equation relates X and P. If you know X, you can find P. Okay? So this is the strategy to solve the problem. This is your step 2. Any questions? Anyone didn't understand the logic behind how the problem is being approached? All clear? Ayush has a question. Yeah, speak, Ayush.
After step 2, what have you done?
Step 2. This is still step 2. After equation 2 you're saying?
Yes, after equation 2.
Okay. So take this, let's consider flask 1 in the initial and final conditions. Okay. In the initial conditions, I'm writing the equation PV equals nRT. Okay. Or V equals nRT divided by P, correct? Okay, now apply this equation twice. The volume is going to be constant, correct? The volume of the flask is not going to change, right?
Right, sir.
So apply to the first case and the second case. If you apply to the first case, you had 1 mole of the gas initially. It was at 300 Kelvin and the pressure was 0.5 atmospheres, yes?
Right, sir.
In the final case, you had X moles of gas. It was at 300 Kelvin because the temperature of the first flask didn't change, but the pressure had changed to P, correct?
Okay, yeah. Yes.
And therefore, you know X because you have these two equations, right? You can solve for X and Y, two equations, two variables.
Wait, but didn't you get equation?
Yes?
Didn't you get equation 2 by relating the gas equation of the first flask and the gas equation of the second flask?
I did, but so I used the two flasks in the final state separately, so that's how I was able to relate X and Y. Now I'm using the same flask, but the initial and final conditions are different, yes? So the number of moles has become X instead of 1 mole.
Okay. Okay.
Yeah? And if you have equation 1 and 2, then you know X and Y already by now, yes? You can solve for X and Y.
Okay, right. Yes.
Correct? And in this equation number 3, you know X, R is a constant, anyway it cancels out, so the only variable is P.
Okay, okay. Yeah, I understand. Yeah, I got it.
Okay?